types of backends, depends which person you're talking to. If you talk to VLSI designers, for them, the backend is the interconnect. All the metallization and the inter-level dielectric units which are connecting the transistors on chip is called backend. However, if you talk to people in the field of packaging and system, for them, backend is the package. It means the bonding to the package or the packaging from the chip to the final product. So there are two types of backends, and I'm going to, in this talk, I'm going to talk about them both, because both are affecting the performance of future VLSI, and moreover, the boundary between the on-chip backend and the out-of-chip backend are going to be entangled, are going to be mixed because of 3D integration. You're going to integrate chips on the same package, so it's going to be very difficult to decide what belongs to the chip, what belongs to the package. So we called it front end. Front end are the transistors. I made a short list of devices under research in VLSI. You can just see the list. Silicon MOSFET, then you have all these Van der Waals FET, homo junctions, 3,5T FETs, graphene, of course, nano ribbon FET, and then you have ferroelectric FET and negative, and then you have spin FET, and you see that I took it from the paper from 2019 of Dmitry Nikonov, and they presented a very nice paper reviewing all this technology. I'm not going to review these technologies. It's just to show you that there's a lot of activity in fundamental research of the switches. The devices are the switches, but if you look at what's happening currently, the winner is silicon MOSFET. Silicon MOSFET is currently, and silicon is currently the dominant technology. So the top line is the dominant technology. And it's not simple, because if you look at, I took it from the same paper. This is from a paper from Markov from 2014. It's a beautiful picture showing you, like, look at the atomic spacing limits of the device density to one device per nanometer. If you plot a traditional device and the distance between, if this is the source and this is the drain, this distance is can be 100, 130, 90, 130, 65, 180 nanometers. So you cannot, let's say it's much, much larger than the distance between the atoms. If you look at 22 nanometer, which is not new, 22 nanometer technology, and the 22 nanometer is traditionally defined the width, the distance between the source and the drain. And this is distance. At 22 nanometer appeared 5 or 6 years ago. You start to see if the distance between the atoms is in the range of 0.3 to 0.4 nanometer, 22 is only 100 times larger. But if you go to sub 10 nanometer, and today I'm going to show some devices which are 5 nanometer, the distance between, switch to black, the distance between the source and the drain is like 20 atoms on the silicon. So you're talking about a device which is not much, much bigger than the atomic distance between the atoms. So what happens if you reach 3 atoms, 4 atoms? How do you analyze this? What is the meaning of this device? What is the physics of this device? How do you model this device? Because this lecture is about VLSI design, so one of the key issues in VLSI design is how to model the devices, because we all know that when part of the design, how do you design VLSI? You have your idea in your head, you sketch on a piece of paper, then you design it, and you design it on a computer, and then next you simulate it. How do you simulate an MOS device, a sub 10 nanometer device? What is the physics that governs the transport of the atoms from the source, from between the source and the drain. And the real device is even more complicated, because if you look at VLSI design, and all of you that designed VLSI in the past, you know that you take the green side and you plot an active region. This is from the VLSI design point of view. Then you put the poly or the gate, and this defines the gate. This defines the source. This defines the drain. And the rest of it is typically STI, shallow trench isolation. So this is how you design. This is, if you want to design a transistor, this is a transistor. Now, if you go for this is kind of the top view from above on the computer. In real life, the transistor, the source is here, the drain is here, and this is the gate. And the gate is controlling the transport of the electrons in NMOS and holes in PMOS. And this is practically a switch. It can be closed, it can be open. This is open, and this is closed. So this is the switch. Currently, in some companies, people switch to a FinFET device, and this is the silicon. The silicon looks like a fin of a fish or shark, and the gate is around it. And because the gate is around it, we got much better current. I'm not going to give you the whole physics, but everybody knows that the current in the transistor is proportional to the width of the device divided by the length. The length is the distance between source and drain, or this distance inside between source and drain. So you want L to be small, and you want W to be large, because you want high current, because the current is related to, if we charge and discharge capacitor, C dV over dt is related to the charging current. So if I want dV over dt very high, because I want very fast devices, I want C to be small, I want dVd to be high, and I want I to be high. So in an MOS device, this is W, 1, 2, 3. So W is very large. Distance is the same as a regular device, so we get much higher current. So FinFET is becoming a kind of a dominant technology today, and more companies are doing it, although some other companies or some other products are taking a different approach. As I told you, if I want to make faster devices, I want the capacitance to be small. So one way to do it is eliminate this. We have here a junction. This is the source, and in the source, we have here a PN junction. And this junction has a capacitance. So one way to eliminate the junction capacitance is to eliminate the substrate. So instead of silicon substrate, you make a device which is called SOI, silicon insulator, where you eliminate the silicon substrate and you reduce the capacitance, and you can make the device much faster. So these two technologies, the FinFET and the SOI, are the two dominant technologies for future VLSI. And let's go again a little bit to the physics. We have a source, and we have a drain, and if we plot it from the energy band diagram, the electrons here, to go from here to here, they have to jump over the barrier here. However, they can also tunnel. So if we look at the tunneling distance, if you go to the Heisenberg principle, we can calculate what is the minimum width of the transistors. And here we take some numbers from silicon, like effective mass, and here the energy barrier, I don't take, if previously I took 17 milli electron volt, I'm not taking this number, I'm taking 50 milli electron volt, which is more reasonable number for the barrier if this is a silicon PN junction, because the barrier of silicon, the band gap of silicon is about 1 electron volt. So this barrier, if we take it half the band gap, we get a critical length of MOS devices 4 nanometers, which means You see, previous calculation, we got 1.5 nanometer. This calculation, we got 4 nanometer. We got the feeling that if we start to put the dimension of the gate less than 5 nanometer, we start to see quantum tunneling effect. It means electrons here, we start to tunnel, and the switch will start to have leakage, which means the barrier from the tunneling point of view is in the range of not far below 5 nanometers, 4 nanometers, 3 nanometers. As I told you before, the layout of the device is, and here I apologize for not keeping the color scheme. So this is the active region, and this is the gate. So if you do this layout, you have one transistor here, one transistor here, one transistor here. So this is like a NAND structure. And we define 2F as this pitch. And if the gate is about 4 nanometers or 3 nanometers, the pitch will be in the range of 6 nanometers. So this will be like the minimum size of the cell for a NAND circuit. So let's move on and talk about other barriers. Listen, when I teach this class and I look at all the barriers, just talking about the barriers, the limits for computation, takes about 6 hours because there's a lot of limits. The limits, the fundamental limits in manufacturing, like the diffraction for lithography and Amdahl and all these barriers. We have the material issues, which are the electric constant mobility, morphology. We have the device barriers like the electric. We have the circuit barriers like delay, inductance, thermal related, yield, reliability. And then we have the system and software like specifications, implementation, validation cost. Then we have all these design and validation issues, energy, time, space-time, information. There's a lot of barriers. However, we have only 1 hour, so we skip this very complicated slide and summarize the theoretical limit of scaling. I took it from this lecture by George Buriano from Intel. They presented this a few years ago. In summary, we have the thermodynamics limit, the quantum mechanics limit. Then we have the ultimate limit, which we say, if we are very optimistic, it's in the range of 1.5 nanometer per device, which means this is not, it's not 10 to the 3, 5 to 10 to the 3 transistor per, no, this is a mistake. It's there's a missing number here. It's not to the 3, because this is 1.5 10 to the minus 7. So it's 5, it should be 21 here. 5 times 10 to the 21 transistor per centimeter cube. And this is the limit for the switching speed, and this is the switching energy, and this is the minimum power per bit. So these are the limits. Now, if we go for the physics of the transistors, there are 2 key variables for our devices are the gate materials and the oxide thickness and the supplied device, and we want them to be smaller and smaller and smaller. We want to make smaller VDD, we want to make smaller devices. When we have to do a lot of the design regarding the depletion region, we have a lot of the design. For example, if this is the depletion region in the drain, we don't want it to touch the depletion layer of the source. If we touch it, we got some leakage. So there's a lot of things to do from the, not only from, until now I talked about kind of abstract limits. Next is you need to apply it for the real design of the transistor. So in summary of this device, if you just make the device smaller, it's not enough. We need to change the device if you want to have better device system in the far future. Now, let me give you some pictures of how a real device looks. This is the FinFET. This I took from the website of ChipWorks, which is a company